Hello everyone, my name is MD Niamul. I am a PhD research student of Mechanics of Advanced Materials Research Group from Wolfson School of Loughborough University, UK. And today I'm going to share my research work on dynamic fracture behavior of additively manufactured polymers and composites under ballistic impact. Before going straight into my research, I'd like to provide some background knowledge on the process of additive manufacturing. So, additive manufacturing or 3D printing is a layer by layer adhesion of materials to manufacture different structures. The advantage of the process is the ability to fabricate complex architectures with reduced material waste compared to conventional manufacturing techniques. The type of materials that can be used for this process ranges from metal alloys to ceramics and polymers, and the different techniques involve fuse deposition modeling, powder bed fusion, stereolithography, etc. Significant research have been carried out on the quasi-static performance of additively manufactured materials. However, studies on dynamic performance of these materials are quite limited, especially for 3D printed polymers and composites. The aim of the research is to understand the dynamic performance and fracture behavior of these materials under impact loading and model these behaviors using finite element analysis. This would allow us to optimize the structures based on their application. For example, prosthetics for medical application, protective gears for sports technology and body armor, as well as impact-resistant parts in automobile and aerospace industries. The first step of the research was to select the material to investigate and the method to fabricate the structure. This was followed by a series of mechanical tests to characterize the material and get its property for such fabrication technique. Then a series of ballistic impact tests was carried out to understand its fracture behavior under dynamic load. And finally, numerical modeling using finite element analysis was carried out with present damage model and compared with experimental results. For the research, nylon filament reinforced with short carbon fiber was selected, and the printing method was fuse deposition modeling. This method heats the filament and melts into a semi-liquid phase, which is then extruded through a nozzle. The material solidifies and adheres to corresponding layer, forming a multi-layered composite structure. Nylon was selected as the material because it shows more plasticity compared to other polymer like PLA or ABS, therefore would absorb more energy through deformation before failure, and the addition of carbon fibers significantly increases the strength of the material compared to just the polymer itself. The Ultimaker 2 Plus printer was used to print the samples for testing, and the following key parameters were selected for the printing process. The nozzle temperature was 260 degrees Celsius because of the high melting point of the material. The print bed temperature was 50 degrees Celsius for adhesion of the material with the print bed while printing. The nozzle diameter was 0.8 mm to avoid clogging issues, and the layer height was 0.125 mm to maximize the amount of fiber in the layers. Finally, the print orientation of 0 degree, 45 degree, 90 degree and minus 45 degree was repeated among the layers to achieve a quasi-isotropic structure. For the mechanical characterization of the material, the tensile test was carried out as per ASTM D638 using a 2 mm thick specimen. The following tensile stress versus strain graph was obtained. From the graph, it was calculated that the tensile modulus is around 1.97 gigapascal and the tensile strength is 53.79 megapascal for the printed structure, and the area under the curve revealed a toughness of 5.15 megajoule per meter cube. After the test, observing the specimen showed a clean fracture, indicating a brittle failure. The compression test of the material was also carried out as per ASTM D695, and the following compressive stress versus strain graph was obtained. From the graph, it was found that the compressive modulus of the material is around 1.84 gigapascal and the compressive strength is 164.72 megapascal. The average compressive toughness is approximately 36.73 megajoule per meter cube. Examining the sample after the test revealed buckling before failure, which dictates the poor performance of the material under compression. In future, the aspect ratio of the sample needs to be changed and retested under compression. Finally, the dynamic mechanical analysis under 3-point bending test was carried out as per ASTM D5023. A frequency sweep was carried out from 0 to 150 Hz. The average storage modulus ranged from 4 gigapascal to 4.5 gigapascal. The loss modulus ranged from 200 megapascal to around 250 megapascal. And finally, the tan delta of the material averaged around 0.045. Having the properties of the material, few initial ballistic impact tests were carried out, ranging from 96 meters per second to 120 meters per second. A gas gun was used for the experiment with steel spherical bullets of 9 millimeter diameter. Calculating the energy for such velocity ranged from approximately 14 joule to around 20 joules. After the impact test, looking at the backside of the plate shows significant delamination, which is the main failure criteria of this material. This indicates poor bonding strength between the layers in the material, which could be due to the porosity created between the filaments during the extrusion process. The experimental boundary conditions were modeled in Abacus software using finite element analysis. The steel bullet was given an impact velocity of 100 meters per second, which is around 15.5 joule of energy. Hashing damage failure criterion was used for the analysis. The result shows a ductile failure at the back of the plate, indicating delamination failure criterion must also be implemented in the model to match the experimental results. So to summarize, the aim of the research is to understand the dynamic fracture behavior of additively manufactured composite under ballistic impact. Nylon reinforced with short carbon fiber and fused deposition modeling were selected to fabricate the structures. Mechanical characterizations were carried out using tensile and compressive test, including DMA to assess the material elastic-plastic properties. The initial ballistic impact tests were carried out to understand the fracture behavior of the material. And finally, numerical modeling was carried out using finite element analysis with the VUMAT of Hashing damage criterion and compared with the experimental results. The future work will focus on microsity of the printed structure to look into the porosity and its effect on the strength of the material. More mechanical characterization tests such as 3-point bending test will be carried out. The ballistic impact test will be repeated with thicker plates and higher impact velocities. And finally, numerical modeling will be carried out using different failure criteria such as delamination failure using cohesive zone elements. Thank you for listening to my presentation. I'm happy to take any questions now.